All right, here we go. 4.3, second derivative test. So these derivatives tell us something about the original function, and you'll see we're in Calc 2 we'll go up to the fourth derivative, I think the sixth derivative. So these derivatives, as we generate them, tell us something about the original function. So this particular derivative tells us about the concavity of the original function. Test for concavity. For inflection points. And for possible local min or max. So 3 things to conclude here. A little bit longer than a first derivative test. On your exam, I will say, just do a second derivative test for concavity. Just do a second derivative test for inflection points. Just do a second derivative test for local mins or maxes. Okay? I'm not going to make you do one big problem, right? Because I want you to have different functions, so I could do a second derivative test with 2 different functions, one to find concavity, one to find inflection points. So let's first of all look at what I mean by concavity, right, and inflection points. So just imagine I had y equals e to the minus x squared, right? We should know what that one looks like by now. This is my bell curve. Right? And so first derivative test, I'd have a critical value where? At what x value? 0, right? Because I have a horizontal tangent at 0, right? So, by the way, when I do a second derivative test, I find the criticals of the first derivative as well, okay? Now, can you see where this thing looks like a smile? So on this left piece, it looks like a smile there. Do you see the smile? When the second derivative is positive, positive people smile. This is somebody who is good energy. I would say they're up. I see concave up. And so that's happening over here too. Do you see that smile over on that right side? That means f double prime of x is positive, right? Positive people smile. Concave down is here. You see the frown. Concave down. Frown. What's the second derivative going to be? Negative. Negative people are frowning. Let's get them out of our life, right? Get rid of those people. Sometimes they're your family, so it's hard to get rid of them, but eventually you only have to see them at holidays. Concave down. So down is the frown, up is the smile, right? And then it happens that I have 2 inflection points. If you imagine we're up in a helicopter looking down on the ground. So this is a road, right? This is a road moving like this, right? Do you see it? It's a road like that in the ground. You watching me? It's a road. I'm not going up a hill, right? I'm looking at the map of the flat surface. So I'm turning, right, on the road. You with me? What am I turning originally? Which way am I turning my wheel? To the left. When I hit that first inflection point, now I'm turning to the right. You can see that concavity happening to down, right? And then I'm turning back left again at the second inflection point. So this is where the change in concavity happens, right? The change in concavity happens and the point exists. So if my second derivative changes from positive to negative at some critical value c, then and c, f of c exists, then I have an inflection point. Notice the first derivative, we said we had a critical value of 0. Look at the sign I'm going to get when I put that critical value in the second derivative. So x equals 0 is a critical of f prime, right? F double prime of 0 is what? Positive or negative? At 0, I'm at this point, right? What's the concavity there? Down, so it's negative, right? So if you think about it, where do I have to be? At the top of a hill. I have to be at the top of a hill. If it's concave down, on top is got to be a max. So if my second derivative of a critical of the first is negative, then I could have a possible local max. Question, Claire?
So, the word inflection, when you're saying inflection points, is always referring to
Change in concavity.
the change in concavity.
Yes.
Yeah, okay.
Yes.
Okay, awesome.
Yes. I like to think of the road. Change in my steering. What do you think? You can see it's the very similar process. It's just a little bit longer. So let me write out a step by step. Let's do a couple of problems, right? So we're going to start with graph f of x, right? Say again? Yes. So graph f of x, right? Possibly think about the domain, think about first derivative criticals where you have a vertical tangent, a horizontal tangent. Think about the domain, right? Whenever I'm graphing, I'm thinking about everything from pre-cal, right? All those things that we told you to think about from pre-cal. Find f prime of x and the C1 values. So critical values of the first derivative test. Remember, I'm going to do a second derivative, so I need to find the C2 values. I need to find the criticals of the second derivative, right? Note if C1 comma f of C1 exists or not. Because if it doesn't exist, it can't be a local min or max. If it does exist, it can be a local min or max, right? So I want to make sure I find my critical values of the first derivative and see if they exist in the original function. I can't stand at the top of a hill if there's a hole at the top of the hill. I fall in, right? All right, graph. Find the first derivative and the critical values. Step 3, find f double prime and the C2 values. Right? Find the critical values of the second derivative. Create your number line sign table separated by the C2 values.
You probably already went over this. I'm so sorry. What is C1 and C2?
Well, the 1 is referring to the first derivative, and the 2 is referring to the second derivative. Yeah. Create the number line sign table using the critical value. I want to say C2 values instead of saying the critical values from the second derivative. That's why I'm shorting, right? Using the C2 values. And when possible, test with the C1 values. So I'd like my criticals of my first derivative to be test values. Why? Because what I said before, if it's concave down, I could be at the top of a hill. So I'm seeing if my second derivative is positive or negative at the criticals of the first derivative. Right? Pick test values and fill in the signs of f double prime on the number line. It's the same as what we did with the first derivative. It's just a little bit longer. We're ready to talk about the intervals of concavity, right? State the intervals of concavity. Using the sign of f double prime, right? Where the second derivative is positive people smile, we know we're concave up. Where the second derivative is negative people frown, we know we're concave down. State possible inflection points. What has to happen? F double prime must change signs and C comma C2 comma F of C2 must exist. I need that critical value of the second derivative to exist on the original function. Right? I need there to be a point where I had a critical value. State possible local min or max. So for example, f double prime of C1 is positive, C comma F, C1 comma F of C1 exists, then C1 comma F of C1 is a local min. If I get a positive value out of my second derivative, the point that I tested at is got to be at the bottom of the hill. As long as that point exists, right? If I get a second derivative that's negative, the point that I tested at from the first derivative has got to be the top of the hill, as long as it exists. Oh my God, it just gives me a headache thinking about it, right? Ugh. I'm sorry. I mean, I know the whole class is tough, but I'm sorry, it's also sometimes tough and very boring.
So when we're tested on the first derivative test and the second derivative test, we're not going to have access to the these steps.
What on the quiz?
Yeah, on the quiz.
Yeah, I'll let you use a formula sheet on the quizzes from now on. Formula sheet on the quizzes from now on, okay? Local min. If my second derivative is positive, you see I'm at the bottom of a hill, so that's a min. If second derivative is negative people frown, I'm at the top of a hill. It's counterintuitive, so don't use your intuition, write it down. Right? Use your cheat sheet. And of course you're going to know you're right because it's all going to show up on the graph. Right? It will all show up on the graph. All right, so let's do this with the exact function I just had, e to the minus x squared, right? We ready to go? Everyone okay? Anybody need a moment? And just to make sure everyone heard it again, I gave you a first midterm on chapter 2 and 3. I'm giving you a second midterm on 4 and 5, right? If your final exam is higher, the lowest one of those two tests will be replaced by your final exam if it's higher than those tests. So there's a chance for this first test you took for me to not count at all. You understand this? Good. All right, let's do a second derivative test complete for e to the minus x squared. Nice. We already know the graph, which is kind of nice, right? It's that bell curve. Pretty important curve, especially if you think about statistics or curving a test. What does it mean for curving a test? For every A, there must be a what? For every A, there must be an F. For every B, there must be a D. And what's in the middle? The C's. That's a real curve. In high school, we didn't curve. We just added 10 points to everyone's grade. Right? That's not a curve. In college, if they curve your test, if there's 3 A's, there's 3 F's. Even if the highest score is 40 out of 100. So careful what you want, what you ask for when you, right? Okay, so what do we need first? Our first derivative, right? So first derivative is pretty easy. It's just a chain rule problem. I get negative 2x e to the minus x squared. Everyone agree? And I need the criticals from this. I can think of a numerator and a denominator here, right? This is negative 2x over e to the x squared. Well, the denominator is never 0, right? E to the x is never 0, so if I do e to the x squared, that's also never 0. So f prime of x equals 0 implies negative 2x equals 0, implies x equals 0. Note that f of 0 is e to the 0 is 1 is a real number. So I know that's a possible min or max. Right? What would I need? I need the first derivative to change signs from positive to negative, or I need my second derivative to be negative. They tell me the same thing. All right, we ready? Second derivative? Good, you're not copying me. Right? So I'm doing a product rule here, right? Yeah, did you get something different? Yeah? More? I mean, I just used my first derivative to get it, right? Anybody else get it? Nice. F double prime of x exists everywhere, right? But it does equal 0 a couple times. So f double prime of x equals 0 implies 2x squared minus 1 equals 0, which is x equals plus or minus square root of 2 over 2. Right? I get x squared equals 1/2 and I square root 1/2. Right? I get plus or minus square root of 2 over 2. These are my critical values of the second derivative, right? So I'm ready to set up my number line, right? Remember, I know what my function looks like, right? I can see it's the whole number line, right? And I'm thinking that where I'm turning on this curve is my plus or minus square root of 1/2, square root of 2 over 2, right? So the number line is coming from my two critical values minus rad 2 over 2 and plus rad 2 over 2. And I want to come up with criticals, right? So square root of 1/2 is easy to find a number smaller than it, right? What can you think of a number smaller than the square root of 1/2? -1. If I can take integers, I will, right? Is that right? Yeah, -1, right? Square, help me. Square root of 2 over 2 is what? Yeah, it's less than 1, right? So 1 and positive 1 will work. And what do you want me to pick for the critical in the middle? 0, because that was my critical from the first derivative. I want to use my criticals from the first derivative as test values for my second derivative test when possible. And so the question kind of becomes, are they always going to be possible test values? Which means a critical value of the first derivative, right, cannot be a critical value of the second derivative. Why? That's always a question on my test for extra credit. So I won't answer that. Think about it. Why can a critical value for the first derivative not be a critical value for the second derivative? I don't want to hear an answer. Think about it. All right, I'm going to do my second derivative signs now, SIGNs, right? Do I need to plug these values in? Hell no. I can already tell my function starts concave up. Positive people smile. And then in the middle, it's concave down. Those are the frowners, right? And then it's concave up again. I'm done. I could cheat this part. Is it okay to put the values into the second derivative? Yeah. But you're going to get the same answers, right? Before I write my conclusion, I'd like just to kind of know, are these possible inflection points? Well, my second derivative changes signs at each of them, right? But what is f of plus or minus rad 2 over 2, right? That's e to the minus plus or minus rad 2 over 2 all squared. That's e to the minus 1/2. That's 1 over the square root of e. And that's a real number, right? And that's what I needed to happen. I needed that to happen. I need my second derivative to change signs from positive to negative or negative to positive, right? Ryan, did I make a mistake?
No.
Yeah. So let me look at Desmos here before I write up my conclusion. I know I'm going to get a local max at 0, 1. And I think I have inflection points at negative square root of 2 over 2, comma, 1 over the square root of e. Ha! I love it. I love it when I get things right. And I'm lazy, so I'm going to copy that and put it in my other one and take the negative out from my other inflection point. Yes! This one is not so easy to graph these points on your calculator, but you could kind of trace up to it. You know what I mean? You could try and get the decimals and trace to it to double check yourself instead of plotting a point. You can plot a point on a TI-83 or 84. You need to use the stat menu. It's easily found on the web how to do that. And all your homework you're turning into me, you're turning in a graph. On all your test or quiz problems, you're turning in a graph. Labeled, of course. X-axis, Y-axis, function, any special points, right? Nice, we're ready for our conclusion. And you'll see we have 3 of them. We've got a conclusion for concavity. We have a conclusion for inflection points. We have a conclusion for local mins and maxes. Since f double prime of x is positive on the interval from minus infinity to minus rad 2 over 2 union rad 2 over 2 to infinity. Always open intervals, by the way. Always open intervals. I don't know if I had stated that correctly last time, but I only want open intervals. I'm not interested at the exact endpoint of an interval because I'm just standing there at the exact endpoint, right? I'm not climbing up a hill or climbing down a hill or going over, right? Going over the hill or hitting the bottom of a valley. I'm moving. On a closed interval, I can stop somewhere. On an open, I can't stop anywhere. Since f double prime of x is positive on I, the interval from minus infinity to yada, 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 f is concave up on I. Right? Positive people, smile. Since f double prime of x is negative on the interval j from what? Minus rad 2 over 2 to rad 2 over 2, f is concave down on j. And 0, 1 is a local max. Because 0 is in that interval and it's concave down, so I must be at the top of a hill. Since f double prime of x changes signs at plus or minus rad 2 over 2, and f at plus or minus rad 2 over 2, which was equal to 1 over square root of e, exists plus or minus rad 2 over 2, comma 1 over square root of e are both inflection points. Yuck. Horrible, huh? Nice, let's take a little break. Let's take 10 minutes, come back at 10:25. For quizzes and tests is give you a function that you worked on before, right? Give you a function that you worked on in chapter 3. So you make sure you do first derivative test and second derivative test with every function on your midterm, because that's what I'm going to do. I do it every time, okay? So for example, I kind of think, I have your midterm here. Yes. So I might do something like arctan of 2 over x. But I don't like that one, so I'm going to do another one. Let's do y equals the arctan of x squared, right? So you got to think, what kind of derivatives am I going to make you do? A trig derivative, an inverse trig derivative, an ln function, right? I'm going to make you do something with all of the functions from chapter 3, right? So like what if you look at, if you had your midterm, this was number 7 on the midterm. I had x squared minus 1 squared times an x minus 1 cubed, right? And I asked you to find y prime, right? So what could I do on this particular function? First derivative test, right? So you'd have to be able to do that kind of derivative again. So why do I do that? Because I can see if you missed it on your chapter 3 test, right? And now you can do it. I can really say, wow, I don't think chapter 3 is an issue anymore. I think this student will be fine in Calc 2, right? But if you still can't do that derivative, right? So that's I'm trying to give you second and third chances on everything. All right, do we know what this thing looks like? Well, if you know what tangent looks like, right? This is y equals tangent. You should then know what arctan looks like. And then when I square x in there, what's going to happen? All the negatives are going to do what? Yeah, so it's going to get a little steeper and everything will be above the x-axis. So it looks like I have concave down, concave up, concave down. You agree? Yes? Yeah. Good. Instead of doing the whole thing, let's just find the inflection points. I'd like just to find the inflection points. So what do I need? So find the second derivative and the inflection points. I already know that my derivative, my second derivative, is not going to have any points missing, There's going to be no places where the denominator is 0. How do I know that? Yeah, there's no point missing, right? There's no place where this function doesn't exist. And none of my slopes are infinitely steep, right? So there's no place the derivative doesn't exist. And I know my second derivative points, critical values are going to change where my concavity is, but it's continuous everywhere. So there's no partitioning happening where I separate pieces of the function that are one's concave up and one's concave down. So help me, y prime. Yeah, 2x times 1 plus x to the 4th, right? If you remember, you have a formula y equals the arctan of u. Gives me y prime is u prime over 1 plus u squared. Good. Y double prime, quotient rule. On your mark and set, go. Anybody else get inflection points or critical values of the fourth root of 1/3? Keep working until you get there. what's nice is that I get plus or minus square root of rad 3 over 3. So that's kind of nice because I know what the tangent is at rad 3 over, right? I know what reference angle I'm at for tangent equal to rad 3 over 3. Yes? Who's got that? Yes. Yes. Yes, so I didn't hear that last part, Grace. From there to there? Okay, so first of all, you got that answer, right? Good. Square root both sides. I get x squared equal plus or minus square root of 1/3. So, but I have to then square root again. But I can't take a square root of a negative, so I only use the positive inside. And a half power of a half power is a fourth power. And so that's how I moved over to the fourth power here. Oh, so I rationalize the inside. Square root of 1 over square root of 3 is 1 over rad 3. And then I'm going to do rad 3 over rad 3. So I get rad 3 over rad 9. That's rad 3 over 3. Either way, so I'm saying these are all equivalent. This is equivalent to this is equivalent to this. Why did I finally decide on this one? Because I see my reference angle for arctan. I see my reference angle for tan. Right? What's the reference angle? Pi over 6 or pi over 3? Who agrees with pi over 6? Who agrees with pi over 3? Who can't do trig at all? Who doesn't want to ever do trig again? Don't take Calc 2. Yes, you do. You have a choice. You don't have to study this stuff. Like for my computer scientist, what I already told you is you don't have to go through school, right? You could just hack into Russia and you'd be famous. You'd be a very high-paid hacker working for the government. No more school at all. One more time?
Can I see your second tutor?
Yes. Yep. So what's the answer? Pi over 6? Sine of pi over 6 is 1/2, right? Square root of 3, yeah, pi over 6. So I want to just double check this with my calculator, right? I'm going to do it with Desmos because I think it's clearer. Why can't I open it? There we go. So my function is the arctan of x squared. Nice. Oops. And I had 2 points, right? My criticals were plus or minus square root of rad 3. Yeah, rad 3 over 3, right? So I want minus square root of the square root of 3 over 3, comma, pi over 6. Look at that. Is that a beautiful thing? There's no way you can be wrong on this test. And then I just got to get rid of that negative. There's no way you can be wrong. Right? Everything you can check. The key is, yes, you could be wrong, but don't panic if you are wrong. That's the real trick. Right? That is the real trick. So what happens when you go and you check it on your calculator and realize you're wrong? Well, imagine that, right? You got to be creative, right? So what if you got this? Well, you still see the x value. It looks like your critical value is right, but maybe you got the function piece wrong. You got the height wrong, right? So you gotta think. You got to be quick on your feet. You can look at your work and maybe you can find an error, but most likely you won't be able to. So you try the problem again. You get your second derivative the same. All right, now you know for sure your derivative was right. Your second derivative was right, and it's got to be your work on finding the y value of the inflection point. So you focus on that. What's a nice way of checking that I have my derivative right graphically, right? What's a nice way of checking I have my derivative right? Well, when the derivative is decreasing, when the function's decreasing, the derivative should be negative, right? So let me put in g of x, this is my derivative, equal, remind me, 2x over 1 plus x to the fourth, right? Oops. Look at where the derivative is negative, underground, under the x-axis. Where it's underground, the original function in blue is decreasing, right? And then the blue function starts increasing, and look at the derivative. It's above ground. That's got to make sense to you. So it's a nice way of checking that you got your derivative correct by graphing the function and its derivative. What if I graph the second derivative? Right? What was my second derivative? Please remind me. 2 minus 6x to the fourth. All divided by 1 plus x to the fourth. Oops, I did the same mistake. All of that squared, right? Oops. Doesn't like something I typed in. Let me just type it again. 2 minus 6 x to the fourth, right arrow, highlight, divided by, let me start with my paren, 1 plus x to the fourth, get out of there, raised to the second. There it is. Look at where the blue function is concave down. Down people are negative. The second derivative is underground there, right? The second derivative is underground. As soon as that turned to concave up, look at the green graph. It's above ground. So this is a nice graphical way to know if you've got your first derivative right, second derivative right. Use it. Show me you're using it on the test. All right, I'll be so happy, and you'll know you have it right. I'll give you extra points. Nice. Let me stop my recording here.